Imagine winding back the cosmic clock. Galaxies stream in reverse. Stars grow younger, planets unform, and the structures of the cosmos collapse into tighter and hotter states. Keep rewinding, and after billions upon billions of years, the universe contracts into a state so extreme that ordinary description begins to fail. That place in the timeline, 13,800,000,000 years ago, is what we call the Big Bang. Yet the name itself is deceptive. The words suggest an explosion, as if a great fireball erupted somewhere in the void and spewed fragments outward into the emptiness. The true picture is stranger, far more difficult to capture in simple language. The Big Bang was not an explosion inside space. It was the rapid expansion of space itself. There was no central point where it happened. Instead, every region of the universe once existed in an incredibly hot and dense state, and every region expanded together. It is not that galaxies fly away from some middle point, but rather that the fabric connecting them stretches. Imagine raisins in dough as bread rises in an oven. The raisins are not propelling themselves outward. They are carried apart by the swelling dough. In the same way, galaxies drift apart because the very grid of space-time lengthens between them. This is what modern cosmology means when it says, "The universe began with the Big Bang." This is also why the idea of a beginning is so slippery. When people ask where it happened, the answer is everywhere. When people ask what the universe expanded into, the answer is nothing outside itself, because there was no space beyond the universe to expand into. When people ask what was before, the answer becomes more complicated still. According to general relativity, which is the framework Einstein introduced in the year 1915, time and space are woven together into a single fabric called space-time. If space-time itself had a beginning, then asking what happened before is like asking what lies north of the North Pole. The question assumes a direction that does not exist. The standard model of cosmology, known as lambda cold dark matter, explains much of what we observe today. It combines Einstein's equations of general relativity with the idea that on large scales, the universe is homogeneous and isotropic. That means it looks the same everywhere and in every direction when averaged across billions of light years. In this model, ordinary matter, the atoms that make up stars, planets, and people, account for only a small fraction of the total. Dark matter, an invisible form of mass that interacts through gravity, provides the glue that holds galaxies together. Dark energy, represented by the Greek letter lambda, drives the acceleration of cosmic expansion. Together, these components form a picture that is remarkably successful. It explains the distribution of galaxies, the cosmic microwave background radiation, and the way light bends under the pull of mass. The cosmic microwave background itself is like a photograph of the infant universe. It is the afterglow left from a time when the universe was only 380,000 years old, when atoms first formed and light could travel freely through space. Before that time, the cosmos was an opaque plasma of particles and radiation. Afterward, it became transparent, and that ancient light has been traveling ever since, stretched into microwave wavelengths by the expansion of space. Astronomers measure it today as a faint glow that fills the sky in every direction, a perfect reminder that the universe truly did begin in a hot, dense state. Yet for all its success, the standard model is silent about the very beginning. It describes what happened after the first fraction of a second, but not the origin of space-time itself. Push the equations backward, and they lead to a singularity, a point where density and temperature become infinite and the laws of physics collapse. At that edge, our familiar concepts of space and time lose meaning. This is where the question of before emerges in all its difficulty. If time itself began, then perhaps before is not a sensible word. But human imagination resists this conclusion. We want to know what lay behind the curtain. We want to know whether the Big Bang was truly the beginning, or whether it was the latest chapter in an older, perhaps eternal, story. In the 20th century, cosmology underwent revolutions that brought us closer to this mystery. Edwin Hubble's discovery in 1929 that galaxies are receding revealed that the universe is expanding. Later, the detection of the cosmic microwave background in 1965 confirmed the hot origin model beyond doubt. Since then, increasingly precise satellites, from COBE to WMAP to Planck, have mapped that glow in exquisite detail, revealing subtle ripples that grew into galaxies and clusters of galaxies. These ripples, quantum in origin, stretch back to the earliest instants of the cosmos. They whisper to us of processes that occurred when the universe was a fraction of a second old. And so the scientific picture is clear. Space and time, as far as we can measure, had a beginning about 13,800,000,000 years ago. Everything we see, every star, every planet, every molecule, is the product of that expansion. But clarity brings paradox. To ask about before is to stand at the edge of knowledge, staring into a region where our equations collapse and our words falter. Still, humans are stubborn seekers. Philosophers, physicists, and poets alike continue to ask. Even if the question itself bends language, it remains the most natural one of all. What, if anything, came before? The human mind has always been uneasy with beginnings that arrive from nothing. When we hear that the universe began, we instinctively imagine a clock that was already ticking, a backdrop of empty space waiting to be filled. But according to general relativity, that backdrop did not exist. Space-time itself unfolded with the Big Bang. This is why cosmologists are careful to remind us that the Big Bang is not an explosion in space, but an expansion of space. It was the coming into being of the very arena in which time flows and matter takes form. Think of time itself as a river. The Big Bang is not a waterfall where the river plunges into nothing. It is the very spring where the river begins. To ask what happened before is to walk upstream beyond the spring. There is no channel there, no water flowing, no direction that can be traveled. In this sense, the question dissolves. And yet, the question persists. Humans do not easily accept limits. When told that time had a beginning, we imagine another layer, a larger riverbed beyond the spring, or a hidden landscape that fed the water before it emerged. The equations of Einstein's theory encourage this curiosity even as they resist it. When we trace the expansion backward, the mathematics describe densities that grow without bound, curvatures that become infinite, and times that shrink towards zero. This mathematical singularity is not a physical object. It is a sign that our description has broken down. Just as the word horizon marks the limit of what we see, but not the end of the world, the singularity marks the edge of our equations, but not necessarily the end of reality. Something existed there, though we cannot yet say what. Some scientists argue that we should stop at that edge. They suggest that physics can describe only what unfolds after the first fractions of a second, that questions about before are metaphysical rather than scientific. Others disagree. They believe that new physics, beyond general relativity, may eventually illuminate that hidden realm. In this divide lies one of the most profound tensions in modern thought. On one side stands the humility of admitting the limits of knowledge. On the other side stands the audacity of believing that even the origin of time may someday be grasped. History shows how often such audacity has paid off. Centuries ago, it was unthinkable to know the age of the Earth. Yet geology revealed its deep history. It was unimaginable to know the age of the cosmos. Yet astronomy gave us a number, 13,800,000,000 years, with surprising precision. Perhaps the next step, as ambitious as it seems, will be to discover the conditions from which the universe itself arose. To reach that frontier requires not only observation but new ideas, ones that stretch the very meaning of time and existence. Already hints have appeared. Quantum physics, the strange framework that governs the behavior of particles and forces at the smallest scales, suggests that space-time may not be fundamental. In quantum mechanics, particles do not have definite positions until they are measured. Instead, they exist in superpositions, possibilities that only later resolve into outcomes. Some physicists believe that time itself may be like this, not a background that always flows, but a property that emerges from deeper laws. If that is true, then the question of before becomes even more puzzling. How can we speak of before when time itself might be an emergent illusion? These ideas sound abstract, but they echo in every observation we make of the night sky. Each galaxy we see receding carries us further back in time. Light from the Andromeda galaxy has traveled for 2.5 million years. Light from galaxies at the edge of our instruments has traveled for over 13 billion years. Look deep enough, and we are staring into the dawn of creation. The telescope becomes a time machine, showing us the history of the universe written in photons. Yet even this machine halts at the cosmic microwave background, the wall beyond which no light can pass. Beyond that veil, we cannot see directly, but perhaps mathematics can serve where telescopes fail. The paradox is that we may never fully escape our language. To describe origins, we say the universe began. To describe limits, we say time started. These are human words, shaped by daily experience, not by the extremes of physics. They carry the weight of common sense, but common sense falters in the presence of infinities. The reality may be something for which no word exists. Still, as creatures bound to language, we circle the mystery with the tools we have, carving metaphors that hint at what cannot be captured. In this way, the question of before is as much philosophical as scientific. It forces us to confront not only what the universe is, but also what it means to ask a question. When we ask what was before time, are we making sense? Or are we chasing a shadow of grammar? Some philosophers argue that the question is meaningless, like asking, what color is the number 7? Others argue that even if the words strain, they point to a real mystery, a truth, waiting beyond the horizon of thought. As we stand here, 13,800,000,000 years after the beginning, our position is humbling. We live on a small planet, orbiting an ordinary star, circling the center of a galaxy that is one of hundreds of billions. Yet from this small corner, we dare to ask about the origin of everything. The question of before is not idle curiosity. It is the deepest attempt to understand our place, to know whether the universe has always existed or whether it truly burst forth from a moment of creation. The search will demand new theories, new mathematics, and new ways of thinking, and perhaps it will demand new words, ones not yet invented, to describe realities beyond the reach of our present imagination. Every path of thought returns us to the same threshold, the singular beginning where our theories falter. If the Big Bang was the true start of space and time, then there was no before. The river began at its spring, and the spring itself has no earlier source. But if the singularity is only a sign of missing knowledge, then perhaps before does exist, hidden behind the veil of equations not yet written. This duality of answers defines the modern struggle with cosmic origins. The difficulty is not just scientific, but also deeply psychological. Our minds are trained by daily experience to think in terms of cause and effect. Every fire has a spark, every wave has a wind, every child has a parent. To be told that the universe had no cause and no time before its first moment is to run against every instinct of reason. This is why myths of creation appear in every culture, from the cosmic eggs of ancient Greece and India to the sacred word of Abrahamic traditions. The human imagination insists on a story of origin. Science, even as it strips away myth, cannot escape the same demand. It too must tell a story. Its story, however, is built not on poetry but on equations, and those equations run into silence at the beginning. Still, even silence speaks. It tells us that our frameworks are incomplete. General relativity, brilliant though it is, cannot be the whole story. It describes gravity as the curvature of space-time, but it does not blend with quantum physics, which governs the other forces of nature. At ordinary scales, this mismatch does not matter, but at the origin, where densities and energies were extreme, both theories must be applied together. Their failure to coexist is a clue. It suggests that at the beginning, physics was governed by a deeper law, one that transcends both relativity and quantum mechanics. The search for that law is one of the greatest quests of our age. In that search, the question of before becomes a compass. If we find that time truly had a beginning, then physics must explain how time could arise from timelessness. If we find that the universe is cyclic, reborn from previous epochs, then physics must describe the mechanism of bounce and renewal. If we find that our universe is one bubble in a larger multiverse, then physics must stretch beyond our horizon to encompass the eternal inflation of countless domains. Each possibility points to a different answer, yet all emerge from the same human urge to know what lies beyond the first moment. There is a strange beauty in this urge. To contemplate the beginning of everything is to stand outside ourselves, to recognize that our lives, brief and fragile, are part of a story measured in billions of years. The expansion that began with the Big Bang is still underway, carrying galaxies apart at speeds measured in thousands of kilometers per second. Our own galaxy, the Milky Way, is racing through space even as we speak, its stars circling a black hole at the center, with periods of hundreds of millions of years. Against such scales, our individual concerns seem tiny. Yet, it is precisely from this smallness that the greatest questions arise. Imagine again the cosmic rewind. Stars collapse back into clouds, galaxies contract into glowing points, light shortens into blinding brilliance, and all of it converges into a state where energy and matter blur together. At the final instant, as the equations fail, we are left with silence. Some call it a beginning, others call it a horizon of ignorance. Perhaps both are true. Perhaps the beginning of time is not the absence of reality, but the presence of mystery. This is why the question of before matters. It is not only a scientific inquiry, but also a philosophical mirror. It asks us to consider the limits of thought itself. Can there be a cause without time? Can there be existence without space? Can nothing give rise to everything? These are not just puzzles for physicists. They are riddles that touch the heart of human existence. Whether we answer them or not, they shape the way we see the cosmos and our place within it. The Big Bang is therefore both an answer and a question. It explains the expansion of the universe, the formation of galaxies, the glow of ancient light that fills the sky. But it also opens a door to the unknown. What came before, if anything, remains hidden. Perhaps there was no before. Perhaps there was a realm outside time. Perhaps the universe itself is infinite, looping in cycles beyond imagination. Each possibility stretches our understanding, and each keeps alive the wonder that drives science forward. As this chapter closes, we remain at the threshold. The Big Bang stands not as a final explanation, but as the beginning of inquiry. It is the stage upon which other theories will unfold, from quantum creation to cyclic rebirth, from eternal inflation to timeless existence. For now, we hold the paradox in our hands. Time began, yet we still ask what was before. The question may not make sense, yet it refuses to disappear. And in that refusal lies the spark of discovery, the restless fire that has carried humanity from caves to stars, and that may someday illuminate even the birth of the cosmos itself. Picture time as a great ribbon unrolling from the past into the future. Every heartbeat, every orbit of the Earth, every flicker of a star adds to its length. We live within this ribbon, carried forward moment by moment, yet when we trace it back, there comes a point where the ribbon itself vanishes. That vanishing is the Big Bang. In the theory of relativity, time and space are not separate stages on which matter plays. They are threads of a single fabric called space-time. Gravity is the bending of this fabric, caused by the presence of mass and energy. The path of a planet around the sun is a curve carved in space-time. The ticking of a clock is the unfolding of space-time at a particular location. Time is not a universal backdrop, the same everywhere. It flows differently, depending on speed and gravity. A clock carried aboard a spacecraft, traveling near the speed of light, ticks more slowly than a clock left on Earth. A clock placed near a black hole ticks more slowly than one in empty space. Time is elastic, stretched and compressed by motion and gravity. If time is woven with space, then the beginning of space is also the beginning of time. The singularity of the Big Bang is not just a place where density grows infinite. It is a moment where the very concept of before loses meaning. To ask what was before is to ask for a time outside of time, a contradiction in terms. This is the profound implication of general relativity. The universe did not start in space. It brought space and time into existence together. Stephen Hawking captured this idea in his famous image of the Earth. Ask what lies north of the North Pole, and the question has no answer. The pole is the edge of north, beyond which north does not exist. In the same way, ask what lies before the Big Bang, and the question has no answer, because the Big Bang is the edge of time. Beyond it, there is no before. Hawking's no-boundary proposal made this metaphor even sharper. He suggested that at the very beginning, time behaved more like space, curving smoothly, so that there was no singular edge, no sharp point where it all began. Just as the surface of the Earth has no edge, only smooth curvature, the universe may have had no initial boundary. Time simply emerged without a moment of creation. This picture is deeply unsettling because it means our deepest intuitions mislead us. We expect every event to have a cause. We expect every story to have a beginning. But if time itself is part of the story, then asking about a cause before time is like asking about a chapter before the first page of a book. There is no such chapter, because the book begins at its beginning. The Big Bang may be that first page, written without prelude. This does not mean the mystery is solved. To say that time began at the Big Bang is to describe the limit of our current theories, not the ultimate truth of nature. The equations of general relativity predict a singularity, but singularities are signs of breakdown. They tell us that the mathematics no longer applies. Just as Newtonian physics fails near the speed of light and must be replaced by relativity, relativity itself fails at the extreme densities of the origin. A deeper theory is required, one that merges relativity with quantum mechanics. Until that theory is complete, the beginning of time remains an open question. Yet even within these limits, the idea of a beginning is revolutionary. For most of history, philosophers imagined the universe as eternal, without start or finish. Aristotle believed time had no beginning. So did many thinkers after him. The concept of a universe that suddenly begins, with time springing into being, is not just counterintuitive, it is radical. It changes how we think about existence itself. Instead of an infinite backdrop, we find ourselves in a cosmos with a finite age, a finite story, a ribbon that began to unroll 13,800,000,000 years ago. As our instruments grew more precise, evidence for this beginning accumulated. The expansion of galaxies, the glow of the cosmic microwave background, the ratios of hydrogen and helium in the stars, all point to a hot, dense origin. None of these require an eternal universe. All point to a finite past. The more closely we listen, the more the cosmos tells the same story. The ribbon has a starting edge. Time itself has a beginning. And yet, though the evidence is strong, the mind resists. Can something as vast as the universe truly begin? Can something as fundamental as time truly have a starting point? These questions reveal how deeply we are shaped by intuition. They reveal why the debate over before refuses to fade. To accept that time has a beginning is to accept that there may be no answer to what came before. But to leave the question unasked is impossible. So we walk the line, acknowledging the limits of relativity while searching for what lies beyond it. When we think about time beginning, we must remind ourselves that this is not a beginning like the first day of a new year or the first note of a song. Those kinds of beginnings happen within time. The beginning of time itself is of a different kind. It is not a point preceded by earlier points. It is the boundary where the concept of earlier ceases to apply. The difference may sound abstract, but it is as profound as the difference between a map of the Earth that shows the equator and one that shows the North Pole. At the equator, you can travel further north. At the pole, you cannot. The direction ends there. The same is true with time. The Big Bang is the pole of history. Beyond it, the direction we call before does not exist. This way of thinking runs against every instinct of daily life. Our memories move backward. Our calendars extend indefinitely into the past. Our histories are filled with origins and causes. Even the simplest question, such as why is the ground wet, leads us to an earlier cause, such as it rained, which itself has a cause, such as clouds condensed. We are creatures trained to seek causes. Yet when we reach the beginning of time, the chain breaks. There is no earlier cause, because there is no earlier. The cause is time itself. This is where Stephen Hawking's no-boundary proposal becomes important. In the 1980s, he and James Hartle suggested that at the very earliest stage of the universe, the distinction between time and space may not have existed. Instead, the universe could be described by a kind of imaginary time, a mathematical concept, in which time behaves like another dimension of space. In that description, the universe has no sharp beginning, no singularity, only a smooth curvature. Just as the Earth's surface has no edge but is finite, the universe may be finite, but without a boundary. Time, in this view, is not something that suddenly started. It is something that gradually emerged from a timeless state. The power of this idea lies in how it dissolves the question of before. If there is no boundary, then there is no before to ask about. The universe, simply, island. Critics point out that this proposal is highly mathematical and not yet connected to observable tests. Supporters argue that it offers a way to think beyond the singularity, to replace an impossible infinity with a meaningful geometry. Whether or not it is correct, it challenges our deepest assumptions. It suggests that what we call the beginning may be less like a wall and more like a curve, less like a bang and more like a transformation. If time had a beginning, what does this mean for eternity? Religious traditions have long spoken of eternal existence, of worlds without end, of gods who exist outside time. The idea that time itself is finite resonates with these traditions, though in a different language. Science speaks not of divinity, but of geometry and equations. Still, the echo is there. Both suggest that time is not infinite in the past. Both suggest a boundary to history. The difference is that science seeks to describe the boundary in measurable terms, through radiation and particles, and the bending of space-time. For those who find the idea unsettling, it helps to remember that the finiteness of time does not diminish the universe. 13,800,000,000 years is an expanse almost beyond imagination. Our entire species has existed for only a fraction of that span. The rise of life itself occupies only the latest chapters. From our perspective, the universe might as well be eternal. Yet from the perspective of physics, it is finite, a ribbon with an edge. That edge is what we call the beginning of time. Some philosophers suggest that beginnings are illusions. They argue that our language forces us to imagine time as a line with ends. But perhaps the universe is more like a circle with no first point. Others embrace the beginning, saying that it is precisely what makes existence remarkable. If the universe had always existed, it might feel inevitable. If it began, it feels miraculous. Even if the miracle is only the unfolding of natural law, it still strikes us as wondrous. In either case, the scientific picture is firm. Our instruments see back to a time when the universe was less than 1 second old. We can trace the cooling of plasma, the formation of nuclei, the moment when atoms emerged and light streamed freely. Each of these stages is recorded in the sky above us. Each is written in the glow of the cosmic microwave background and the distribution of galaxies. All point to a beginning, and all remind us that time itself is not an infinite road stretching backward forever, but a story that began in fire. To live in a universe with a beginning is to live with questions that cannot be ignored. Why did time start? What set the first moment into motion? Was the beginning necessary, or was it an accident? Did the laws of physics themselves arise with the beginning? Were they already present in some deeper form? These questions haunt the boundary of science and philosophy. They remind us that even as we map the cosmos with satellites and telescopes, even as we measure the ages of stars, the distances of galaxies, we stand at the edge of understanding, peering into a darkness that may never be fully lit. The idea that time began at the Big Bang does not silence curiosity. Instead, it stirs it further. If the fabric of space-time emerged 13,800,000,000 years ago, then what determined its birth? Was it inevitable, like a stone rolling downhill, or contingent, like a match struck in darkness? When we say time had a beginning, we are not offering a final answer. We are sketching the outline of a mystery. This mystery grows sharper when we realize that physics itself depends on time. Every law of motion, every equation of energy, Every principle of thermodynamics is framed in terms of change over time. If time itself began, then the laws that govern change could not have existed in the same way before. They too must have emerged. Imagine opening a book and discovering that the first page not only begins the story but also invents the language in which the story is told. That is the scale of the puzzle before us. Stephen Hawking once described the universe as a self-contained system, without boundary and without need of anything outside it. In that vision, the beginning of time does not require a cause, because cause is itself a temporal notion. To ask for a cause before time is like asking for a shadow in total darkness. The word no longer applies. This view strips away the need for external triggers or divine interventions. The universe simply is, and its beginning is woven into its being. Yet even in its elegance, this view leaves a human hunger unsatisfied. We want to know why there is something rather than nothing. To say the universe simply is feels like an evasion, but perhaps it is the only possible answer. Our discomfort comes from the way the human brain evolved. For survival, it is useful to assume that every event has a cause. If the bush rustles, it must be the wind or an animal. If fruit falls, it must be gravity or a hand. This instinct to seek causes has served us well, but at the edge of time, the instinct fails. There may be no cause in the sense we understand it. There may only be existence. Recognizing this does not diminish our quest. It deepens it, showing us how much of our thinking is shaped by the narrow band of experience in which we live. Still, there are glimmers that the story may not end here. Quantum physics suggests that at the smallest scales, reality does not unfold in smooth determinism, but in probabilities. Particles can flicker in and out of existence, borrowing energy from the vacuum as long as they return it quickly. Space itself may seethe with fluctuations. If time emerged from such a quantum realm, then perhaps the beginning was not an absolute boundary, but a transformation from one kind of existence to another. In that case, before may not be meaningless after all. It may refer to a state beyond our current physics, a realm where space-time is not yet born, but where the seeds of space-time lie dormant. For now, such ideas remain speculative. They are the frontier where mathematics stretches imagination to its limit, yet they remind us that to say time began is not the end of inquiry. It is the beginning of a deeper search. Just as the discovery that the Earth is round did not end geography but opened a world of exploration, the discovery that time has a beginning does not end cosmology but propels it forward. The horizon of knowledge shifts, and we chase it still. To live with this knowledge is to hold two truths at once. The first is that time, as we know it, began with the Big Bang. The second is that our theories may someday show us a deeper layer where time itself is not fundamental. Between these truths lies wonder. We inhabit a cosmos that is not infinite in age, but that still carries mysteries as vast as eternity. The ribbon of time has a starting edge, yet beyond that edge may lie a realm outside our comprehension. As this chapter closes, we step from relativity into speculation. We accept that time has a beginning in our current understanding. We acknowledge that this beginning raises more questions than it answers, and we prepare to follow those questions into the quantum world, where particles dance in uncertainty and where perhaps, hidden in the haze, the secret of before still waits. Stand at the edge of the Big Bang, as relativity describes it, and you face a wall. The equations collapse into infinities, and the very notions of space and time lose meaning. To go further, we must turn to a different guide, the theory of the very small, the strange and subtle world of quantum mechanics. It is a world where certainty dissolves into probabilities, where particles flicker into existence and vanish, where emptiness itself seethes with activity. And it may be in this quantum domain that the origin of the universe finds its explanation. To understand how, imagine the vacuum not as nothing, but as a restless sea. In quantum mechanics, even the most empty region of space is not truly empty. It is filled with what are called vacuum fluctuations, temporary appearances of particle and antiparticle pairs that borrow energy from the void before cancelling out again. These fluctuations are usually tiny, lasting for unimaginably small moments, yet they reveal that nothingness in physics is not an absolute void, a potential, a fertile ground. humming with possibilities. Lawrence Krauss and other physicists have argued that the universe itself could arise from such quantum processes. In their view, the laws of physics allow for space and time to emerge spontaneously from a state that we call nothing, but that is in fact a quantum vacuum. Just as a particle can appear from the vacuum, so too could space-time itself. This is the essence of the phrase, a universe from nothing. The word nothing here must be handled carefully. It does not mean the absence of laws, the absence of mathematics, or the absence of possibility. It means the absence of space, time, and matter, while still presuming the existence of physical laws that permit quantum behavior. For some, this stretches the definition of nothing beyond recognition. For others, it represents a radical but coherent picture of creation. At scales close to the Planck length, a distance of about 1/10 million trillion trillionth of a centimeter, the smooth fabric of space-time, imagined by relativity, may break down into a quantum foam, a froth of constantly fluctuating geometry. At these scales, time and space may no longer be continuous. Instead, they may blur into probabilities, with tiny universes appearing and disappearing in a haze of possibilities. Our universe, in this view, is one such fluctuation that did not vanish but expanded, stabilized, and grew into the cosmos we inhabit. This idea is startling, but it is consistent with the logic of quantum mechanics. In the quantum world, what matters is not certainty, but probability. The most improbable events can occur given enough opportunity. In the vastness of a quantum vacuum, the chance of a universe emerging may be tiny. Given eternity or an infinite number of fluctuations, even the rarest events become inevitable. Our very existence may be the improbable made real. The difficulty, of course, lies in evidence. We cannot peer directly into the Planck scale, for our instruments are far too coarse. The energies required to probe such scales are beyond anything we can achieve with particle accelerators. Instead, we must look for indirect traces, patterns in the cosmic microwave background, or subtle fingerprints in the distribution of galaxies. If the universe did arise from quantum fluctuations, its earliest moments may carry signatures of that birth. Scientists search for them in the polarization of ancient light, in the shape of primordial ripples, in the mathematical structure of cosmological models. So far, the evidence is incomplete, but the search continues. To say that the universe emerged from quantum nothingness is not to trivialize it. It is to recognize that our concept of nothing is shaped by daily experience. For us, nothing means absence. In physics, nothing may mean potential, a background of uncertainty from which structures can arise. It is a strange kind of nothing, pregnant with possibility, and it forces us to ask a deeper question. If the laws of quantum mechanics existed before space and time, where did those laws themselves come from? If nothing still carries the framework of physics, is it truly nothing at all? These questions show how slippery the boundary is between science and philosophy. Physicists describe fluctuations and probabilities, but the human mind still asks why such laws exist in the first place. Why is there a quantum vacuum instead of no laws at all? Why does reality follow mathematics? These are not questions that experiments alone can answer. They belong to a realm where physics and metaphysics intertwine, where the language of particles meets the language of meaning. Still, the quantum picture has one advantage over classical relativity. It replaces the absolute impossibility of a singularity with the fertile strangeness of probability. Instead of a wall, we face a mist. In that mist, beginnings are possible, even natural. The cosmos may be less a miracle and more an outcome of quantum inevitability. The idea may be unsettling, but it offers a path forward, a way to think about origins without invoking causes outside physics. If the universe could emerge from a quantum vacuum, then what does it mean to say it came from nothing? This question has sparked debates not only among physicists, but also among philosophers and theologians. Physicists may mean nothing as the absence of particles and fields, but still assume the presence of physical laws, a stage of potential where fluctuations occur. The philosopher may reply that such a state is not nothing at all, because it presupposes structure, rules, and mathematics. True nothingness, the philosopher insists, would mean the absence of laws themselves, the absence of even the possibility of existence. The physicist counters that such an absolute void may not be a coherent concept, that perhaps the closest reality offers us is the quantum vacuum, restless and unstable. In this way, the discussion circles, revealing that our words may never perfectly capture the depths of the problem. Consider how particles behave. In quantum mechanics, an electron does not orbit the nucleus like a planet around the sundial. It exists as a cloud of probability, a wave of possible locations until measured. The entire universe, too, may once have existed as a cloud of possibilities, a wave function, describing countless potential states. Out of that haze, one state became real, collapsing into the space-time we inhabit. This is why some cosmologists describe the origin of the universe not as a physical explosion, but as a quantum transition, a shift from probability to actuality. The Planck scale is the stage for this drama. At lengths of roughly 1/10 million trillion trillionth of a centimeter and times of about 10 to the power of -44 seconds, gravity and quantum mechanics collide. Here, space itself may jitter like a stormy sea. Tiny bubbles of space-time may flicker into being, merge, or vanish. The smooth continuum of relativity breaks into foam. If the universe began at this scale, then our familiar dimensions are the result of quantum geometry, crystallizing from chaos into order. Some scientists liken this to a phase change, like water freezing into ice. Above a certain temperature, molecules dance freely, but when the temperature falls, they lock into crystalline patterns. In the same way, the pre-universe may have been a quantum froth, unstable and shapeless, until a transition crystallized it into space-time. From that moment, expansion could begin, and with expansion came cooling, structure, and eventually stars and galaxies. In this analogy, the Big Bang is not a creation from nothing, but a condensation from a deeper state. Others push the idea further. If quantum fluctuations can give rise to one universe, they may give rise to many. Some theories suggest that universes are constantly budding off from the quantum vacuum, each with its own properties, laws, and histories. Our universe may be just one in an infinite foam of universes, each as real as our own, but forever beyond our reach. In that vision, the question of before the Big Bang is replaced by a larger frame, where beginnings happen endlessly and reality is richer than we can imagine. But here, the limits of science appear. We cannot test other universes. We cannot observe the vacuum before time. We can only model and infer. This is why critics caution against declaring that we have explained creation. They remind us that a universe from nothing is not nothing in the absolute sense. It is nothing in the physicist's sense, a state already carrying the laws of quantum mechanics. And so the ultimate mystery remains: why do those laws exist? Why does reality follow mathematics that allows universes to appear at all? Some respond by saying that to ask why laws exist is meaningless, that laws simply are. Others say the question is the most important one of all, the place where science and philosophy must meet. For if the laws are arbitrary, then perhaps they could have been otherwise. If they are necessary, then perhaps there is a deeper structure, an ultimate principle that makes them unavoidable. Searching for that principle is one of the deepest quests of theoretical physics. What is striking is how the quantum view changes the tone of the mystery. Instead of a universe springing into being as an inexplicable miracle, we have a universe emerging as a natural possibility of quantum law. The improbable becomes inevitable when probabilities govern everything. In this way, the birth of the cosmos is not outside physics, but the ultimate expression of it. The strangeness lies not in the fact of existence, but in the nature of the laws that permit existence. For many, this shift is liberating. It shows that the question of before is not forever forbidden, but may find answers in the marriage of relativity and quantum mechanics. For others, it is unsatisfying because it pushes the mystery back one step without removing it. If the universe arose from a quantum vacuum, then why does the quantum vacuum exist? If laws allow universes, then why are there laws at all? We may circle this puzzle forever, yet even in circling we learn. We learn how to define nothing, how to measure the earliest moments, how to test the predictions of theory against the whispers of ancient light. The deeper we explore, the more we discover that the boundary between physics and philosophy is not sharp. It is a twilight zone where the two overlap, where equations and metaphors blend. Here, quantum mechanics does more than calculate probabilities. It challenges the very meaning of existence, showing us that the question of origins is not only about where and when, but about what it means for anything to be. The vision of a quantum origin invites us to rethink what we mean by beginnings. In the classical world of relativity, a beginning is a sharp edge, a singular point where equations fail. In the quantum world, beginnings are more like transitions, shifts of probability from one state to another. The boundary is not a wall but a haze, where possibilities blend and only later resolve into the reality we know. In this haze, instability is the rule. The quantum vacuum is never still. It flickers with uncertainty, restless with fluctuations. Particles appear and vanish. Energy is borrowed and repaid. Even the geometry of space itself may tremble, curving and twisting before smoothing into stability. It is here, some scientists believe, that the spark of the universe was struck, not by external cause, but by the restless nature of quantum law itself. Imagine a pencil balanced on its tip. In principle, it could stand forever, but in practice, the tiniest disturbance will send it falling. The pre-universe may have been like that pencil, balanced in a state of unstable symmetry. Quantum fluctuations provided the disturbance, tipping the balance and releasing expansion. From that moment, space-time unfurled, carrying matter and energy into being. The Big Bang, in this picture, was less an explosion and more a phase transition, a collapse of instability into growth. This way of thinking reframes the question of nothing, absolute nothingness. The absence of even law may be meaningless. Instead, the closest we can imagine is a quantum vacuum, a ground of uncertainty, where existence is always possible. From this ground, the birth of a universe is not a miracle, but an outcome, one that may be rare, but is inevitable, given the restless nature of quantum reality. We may never know why such a vacuum exists, but if it does, then creation is not only possible, but unavoidable. Evidence for this picture remains indirect, but hints exist. The ripples seen in the cosmic microwave background are consistent with fluctuations stretched by expansion. The distribution of galaxies across the sky reflects patterns seeded in quantum noise. Though we cannot see the Planck scale directly, we see its echoes written across the cosmos, like fingerprints left by a hand no longer present. These clues suggest that quantum processes were active at the dawn of time, shaping the universe we inhabit. Still, questions linger. Could space-time itself be a product of quantum entanglement, arising from correlations between fundamental bits of information? Could time itself be emergent, not a background, but a property that appears when many particles interact? If so, then the universe from nothing is also the universe from information, a cosmos whose foundation is not matter or energy, but the structure of relations themselves. Such ideas are bold, and they remain speculative, but they point to a future where the boundary between physics and philosophy blurs even further. What is clear is that quantum mechanics transforms the mystery of origins. It tells us that the impossibility of a singularity may be replaced with the inevitability of fluctuation. It tells us that the universe may not need an external trigger to exist, only the restless instability of quantum law. It does not silence the question of why, but it shifts the focus from causes outside the cosmos to the deep structure of the cosmos itself. Perhaps this is the lesson of the quantum origin, that existence does not rest upon certainty, but upon probability, that what we call nothing may contain the seeds of everything, that the birth of the universe was not the shattering of silence, but the flowering of potential. In this view, the Big Bang is not a singular act, but the unfolding of quantum possibility into cosmic reality. And yet, even as we embrace this vision, we stand at the edge of another mystery. For if quantum law made the universe possible, then what gives rise to quantum law itself? If probability rules everything, what makes probability possible? These questions carry us beyond quantum mechanics into the search for quantum gravity, string theory, loop models, and holographic principles. They remind us that the story is far from finished, that each answer opens new questions, and that the origin of the universe remains a frontier both scientific and philosophical. As we close this chapter, we step from the haze of quantum origins toward the possibility of cycles and rebirth. If the universe can arise from fluctuations, perhaps it can also collapse and begin again. Perhaps our Big Bang is not the first. Perhaps it is one in an eternal sequence of cosmic bounces. With this thought, we turn from the quantum mist to the idea of cycles, the ancient dream of eternal return, reborn in modern cosmology. Picture the universe not as a single story with a first page and a final chapter, but as a book that rewrites itself endlessly. The pages may burn, collapse, or fade, but new pages are written again and again. In this vision, the cosmos is not a one-time event, but a cycle, a rhythm of expansion and contraction that stretches across eternity. This idea, the cyclic universe, is one of the oldest in human thought and one of the most intriguing in modern physics. Long before telescopes and equations, ancient cultures imagined the world as eternal and recurring. The Hindus spoke of vast cycles called kalpas, spans of billions of years in which the cosmos is created, destroyed, and created again. The Stoic philosophers of Greece believed that the universe is periodically consumed in fire, only to be reborn in an endless sequence. The idea of eternal return haunted Nietzsche in the 19th century, who asked what it would mean to live the same life over and over, every joy and sorrow repeated forever. Though these visions were philosophical and poetic, they echo in the scientific models of today, where mathematics suggests that our universe may not be the first, and perhaps not the last. Modern cosmology usually begins with expansion, but expansion does not guarantee permanence. Gravity pulls against it. If the density of matter is high enough, expansion will eventually halt and reverse. Galaxies will slow, stop, and begin to fall inward. Stars will collide, black holes will merge, and the cosmos will collapse into a fiery crunch. That crunch could then ignite a new expansion, another Big Bang, another universe. This is the essence of the Big Bounce model, where every beginning is also an ending, and every ending is also a beginning. For much of the 20th century, this idea was taken seriously. Observations had not yet revealed the mysterious force we now call dark energy. Without dark energy, gravity might have been strong enough to stop expansion. In that case, a collapse seemed natural, and a new cycle possible. But when astronomers discovered in the 1990s that expansion is accelerating, the picture changed. With dark energy pushing the universe outward faster and faster, a collapse seemed impossible. The cycles appeared broken, leaving only eternal expansion. Yet new theories have revived the possibility of a bounce. In models inspired by quantum gravity, the singularity of the Big Bang may be replaced by a bounce, where extreme density does not lead to an infinite crunch, but to a rebound. Loop quantum cosmology, for example, suggests that quantum effects prevent complete collapse, creating a minimum volume below which space cannot shrink. Instead of a singular beginning, the universe passes through a bounce, transitioning from contraction to expansion. In this view, our Big Bang was not the start of everything, but the moment of rebound from a previous cosmic epoch. The ekpyrotic theory, emerging from string cosmology, paints another picture. In this model, our universe is a three-dimensional brain, a surface floating in higher dimensional space. From time to time, our brain collides with another. Each collision releases energy that ignites a Big Bang, creating a new cycle of expansion. The cosmos is reborn not from collapse within itself, but from the clash of higher dimensional worlds. Though speculative, this theory echoes the ancient myth of cosmic fire and rebirth, now recast in the mathematics of strings and brains. What makes cyclic universes compelling is not only their poetry, but their power to answer the riddle of before. If the Big Bang was preceded by a contraction, then before has meaning. It refers to a previous universe, a cosmos as real as ours, but vanished into its own collapse. If cycles extend infinitely into the past, then there was no first beginning, Time stretches without origin, an endless loop with no boundary. The question of what came before is replaced by the recognition that there has always been a before and always will be. This idea challenges our sense of uniqueness. If the universe is cyclic, then our epoch is not special. Countless expansions and collapses have come before, and countless will come after. Stars will rise and fall. Civilizations may flourish and vanish, and yet the great rhythm continues. To imagine this is both humbling and exhilarating. It means that existence is not a fragile accident, but a recurring theme, a melody played over and over in the symphony of reality. But does evidence support such cycles? That remains uncertain. Some cosmologists search for signatures of previous bounces in the cosmic microwave background, patterns that might reveal traces of a universe before ours. Others look for ways to reconcile cycles with the accelerating force of dark energy. The theories are still in development, their predictions delicate, their mathematics challenging. Yet the very possibility that our universe is not alone in time, that it belongs to a sequence of births and deaths, keeps the idea alive. As we step deeper into this chapter, we must ask whether cycles are illusions or realities, whether the cosmos truly rebounds from collapse, or whether expansion is its permanent fate. The answers lie at the intersection of observation and imagination, where physics touches philosophy, and where the oldest myths of eternal return meet the newest theories of modern cosmology. To imagine a universe that cycles endlessly, we must confront the arrow of time. In daily life, time has a clear direction. Eggs break, but never unbreak. Smoke disperses, but never regathers. Stars burn their fuel, but never rekindle it. This direction arises from entropy, the measure of disorder. In every process we observe, entropy increases. If the universe collapses into a big crunch and then bounces into a new expansion, what happens to entropy? Does it reset to zero? Or does it accumulate with every cycle? This problem haunted early cyclic models. If entropy carries over from one cycle to the next, each new universe should be larger and longer than the one before, stretching the cycles into asymmetry. If cycles are truly infinite, this would mean the current universe is infinitely larger than some that came before. Some physicists found this unpalatable, believing it undermined the very notion of perfect recurrence. Others embraced it, suggesting that perhaps the universe is indeed evolving across cycles, each new one broader and more expansive. In either case, the arrow of time complicates the dream of eternal return. Modern approaches try to resolve this by invoking quantum effects. In loop quantum cosmology, the bounce does not preserve entropy in the usual sense. Instead, the very structure of space-time changes, and with it, the rules that govern entropy. In the ekpyrotic scenario, the contraction phase smooths out irregularities, so that when the bounce occurs, entropy does not dominate the new cycle. These models are still under development, but they show how modern physics can reframe an ancient problem. Observations, too, offer challenges. The discovery of dark energy changed the landscape dramatically. With the universe's expansion accelerating, a collapse into a big crunch seems unlikely. Galaxies are not slowing down. They are racing apart faster and faster. If this continues indefinitely, the cosmos will not rebound. It will expand forever, growing colder and emptier as stars burn out and galaxies slip beyond one another's reach. The cyclic dream would end in a heat death, a universe stretched so thin that nothing happens at all. Yet even here, theorists find loopholes. Dark energy itself may not be constant. It may evolve with time, changing its strength, or even reversing its effect. If dark energy weakens or turns negative, gravity could reclaim dominance and pull the cosmos back inward. In that case, a future crunch and bounce remain possible. The fate of the cycles depends on the true nature of dark energy, a mystery still unresolved. What makes the idea of cycles so captivating is how it mirrors patterns we see everywhere else. Stars are born, shine, and die, only to seed new stars. Planets form, shatter, and reform. Life itself emerges, goes extinct, and emerges again. Nature thrives on cycles, and the thought that the universe itself follows the same rhythm feels deeply resonant. It would mean that the cosmos is not an exception to its own rules, but the greatest example of them. At the same time, cyclic models stir unease. If the universe has no beginning, if cycles stretch infinitely into the past, then how do we make sense of infinity? Can there really have been an endless number of previous universes, each giving rise to the next? Infinity is not just a large number, it is the absence of limit, the collapse of counting itself. Philosophers have long debated whether actual infinity can exist in reality. Cyclic cosmology forces that debate into the heart of physics. For those who embrace it, infinity is not a problem, but a liberation. It means the universe does not need an ultimate origin. It simply is, stretching without beginning or end. For those who resist, infinity feels like evasion, a refusal to face the demand for a first cause. In this tension lies the power of cyclic thought. It presses us to reconsider what it means for time to exist at all, whether beginnings are necessary, or whether the absence of a beginning is the deeper truth. The allure of cycles also lies in their echo of human myths, the phoenix that rises from its ashes, the seasons that die and return, the wheel of rebirth in spiritual traditions, all mirror the cyclic cosmos. These metaphors remind us that the scientific quest is not detached from human imagination, but entwined with it. Our models of the universe are shaped not only by equations, but by the deep patterns our minds find meaningful. The cyclic universe bridges the gap between science and myth, offering a story that feels both rigorous and poetic. Still, science demands evidence. The search for signs of previous cycles continues. Some cosmologists analyze the cosmic microwave background for anomalies, circular patterns that might be echoes of a past universe. Others study gravitational waves, hoping to detect signals from a contraction before our expansion. These searches have not yet yielded conclusive results. But the mere act of searching transforms the question of cycles from philosophy into testable science. If evidence is found, it would mean that our Big Bang was not unique. It was an event in a much larger pattern, a chapter in a cosmic saga that stretches beyond imagination. If evidence is not found, the idea of cycles may fade, but its influence will remain. It will remind us that beginnings are not inevitable, that other possibilities exist, that time may not be as linear as we think. To walk through the vision of cyclic universes is to step into a hall of mirrors where beginnings dissolve into patterns. Each mirror reflects another. Each cycle contains the seeds of the next, and the line of time bends into a loop. If our universe is one in an endless chain of expansions and contractions, then what we call the Big Bang is not unique. It is a bridge between what came before and what will come after. The story of creation is not singular, but recurrent. This recurrence challenges our understanding of meaning. If universes arise again and again, does that diminish the value of our own? Or does it elevate it, making our existence part of a grand rhythm that transcends individuality? For some, the idea of eternal return is daunting, a vision of repetition without progress. For others, it is comforting, suggesting that nothing is ever truly lost, that all forms reappear in new guises. Just as spring follows winter, so too might expansion follow collapse forever. The philosopher Friedrich Nietzsche once posed the question of how we would live if every action, every choice, were destined to repeat endlessly. This was his test of eternal recurrence. Applied to the cosmos, it becomes not only a philosophical puzzle, but a scientific possibility. If cycles are real, then every galaxy, every star, every life may have counterparts in past universes, and will have counterparts in future ones, perhaps not identical, but echoing, perhaps not inevitable, but recurring in pattern. In such a cosmos, history itself becomes a wave that rises, falls, and rises again. But physics, unlike philosophy, seeks mechanisms. How does the bounce occur? How does collapse reverse into expansion? Here theories diverge. In loop quantum cosmology, quantum gravity prevents space-time from compressing into a singularity, instead causing a rebound when densities reach the Planck scale. In the ekpyrotic picture, collisions of higher dimensional branes ignite each new cycle. In other approaches, exotic forms of matter with negative pressure allow the universe to contract smoothly and rebound without singularity. Each model provides a different key to the same door, a different way to pass from collapse to rebirth. Whether these mechanisms are true remains uncertain. The mathematics is complex, the predictions subtle, the evidence elusive, yet they share a common ambition: to remove the singularity, to replace the impossibility of infinite density with the possibility of recurrence. In doing so, they extend the timeline of the universe beyond our own Big Bang, granting it a past and a future richer than a one-time event. If the universe is cyclic, then the question of before changes form. Instead of asking what came before the Big Bang, we ask what the previous cycle was like. Did it resemble our universe, with galaxies and stars? Or was it radically different, with other laws of physics, other constants, other possibilities? If cycles are infinite, then perhaps every variation has occurred and will occur again. The multiverse in time becomes as vast as the multiverse in space. Still, the arrow of time remains the puzzle. In our universe, entropy increases, creating an irreversible direction. If cycles repeat, how is the arrow reset? Some theories suggest that the contraction phase erases irregularities, smoothing the cosmos before each bounce. Others propose that entropy is carried into hidden dimensions, leaving the visible universe fresh at each new birth. These solutions are speculative, but they illustrate the creativity of modern cosmology in grappling with timeless questions. For all their uncertainties, cyclic models remind us that the universe need not have a single origin. Time may not be a line, but a wheel. Beginnings may be illusions, disguises for transitions in an eternal process. This thought connects us with the oldest myths, the visions of cycles, in ancient India, Greece, and beyond. It shows that even as science advances with satellites and particle accelerators, it continues to echo the intuitions of human imagination, that creation is not a one-time event, but a rhythm without end. As this chapter closes, we stand between two possibilities. One is that the universe is singular, born once from nothing, destined to expand forever. The other is that the universe is cyclic, reborn endlessly from collapse or collision, destined never to end. The evidence is not yet decisive, but the very act of considering cycles expands our perspective, showing us that before may not be meaningless after all. It may point to a deeper history, one that stretches beyond the horizon of our own beginning. And so, from cycles and bounces, we turn to an even stranger vision, one born not of contraction, but of inflation. For if our universe is not alone in time, it may also not be alone in space. Beyond the edge of our horizon may lie other universes, budding endlessly in a cosmic landscape. To explore this possibility is to enter the theory of eternal inflation, where the multiverse itself becomes the answer to the question of before. Imagine the universe in its very first instant after the Big Bang. Not stars, not galaxies, not even atoms yet exist. Instead, space itself balloons outward at a pace so rapid that in less than a trillionth of a second, it grows from subatomic size to dimensions larger than all the galaxies we can see today. This breathtaking expansion is called inflation, and it reshaped our understanding of the early cosmos. Inflation was first proposed in the 1980s to solve puzzles left unanswered by the Big Bang model. One puzzle was the horizon problem. Why is the universe so uniform in every direction, Regions of space separated by billions of light years are nearly identical in temperature, yet they should never have been in contact, never able to exchange light or heat. Inflation solves this by saying that the regions were once close together before inflation stretched them apart. Another puzzle was the flatness problem. The geometry of the universe is astonishingly close to flat, meaning parallel lines remain parallel across cosmic distances. Without inflation, this would require fine-tuning. So precise, it seems implausible. Inflation explains it naturally, because rapid expansion smooths out curvature, the way air smooths a balloon. Finally, inflation also accounts for why the universe contains no magnetic monopoles, hypothetical relics predicted by particle physics that would otherwise be abundant. The sudden stretching diluted them beyond detection. The beauty of inflation is not only in solving these puzzles, but in predicting new features. It suggests that tiny quantum fluctuations present during inflation were stretched into cosmic scales, seeding the ripples that later grew into galaxies. When astronomers study the faint patterns in the cosmic microwave background, they see evidence consistent with this picture. Inflation, though still a hypothesis, has grown into one of the most influential ideas in modern cosmology. But inflation carries within it a strange implication. In many models, inflation does not end everywhere at once. Instead, it ends locally, in patches, while continuing in other regions. In the places where it ends, bubbles of space form, each undergoing its own hot Big Bang. Our universe is one such bubble. Meanwhile, inflation elsewhere keeps expanding, spawning new bubbles endlessly. This process is called eternal inflation, and its consequence is staggering. A multiverse, a vast landscape of countless universes, each with its own history, possibly with its own laws of physics. If this vision is correct, then our universe is not the whole of reality, but a small pocket in an infinite froth. Beyond the edge of our cosmic horizon, other universes bud and bloom, forever beyond our reach. Some may be similar to ours, with galaxies, stars, and planets. Others may be radically different, with unfamiliar particles and dimensions. The multiverse is not just a poetic metaphor. It is a direct consequence of certain inflationary models, carried forward by the mathematics itself. To imagine this is to expand our sense of scale beyond anything previously conceived. It is difficult enough to grasp that our galaxy contains hundreds of billions of stars, or that the observable universe contains hundreds of billions of galaxies. But to contemplate a multiverse, where universes themselves are countless, is to stretch thought to its limits. We are asked to see our entire cosmos as one bubble in a cosmic sea, one page in a book with infinite pages. The implications are profound. If the multiverse exists, then the question of before the Big Bang changes shape. Our Big Bang was not the beginning of everything, but the local birth of our bubble. Before it, or beyond it, inflation continued, spawning other bubbles. The word before gains meaning again, not in the sense of time before time, but in the sense of universes before ours, universes alongside ours, universes forever multiplying. In this view, creation is not a singular act, but an ongoing process. This idea resonates with the human imagination, for it suggests that the universe is not unique, just as Copernicus dethroned the Earth from the center of the cosmos, and just as modern astronomy dethroned the Milky Way from being the only galaxy, so too does the multiverse dethrone our universe from being the only reality. Each step expands our horizon. Each step humbles us. Each step reveals that what we once thought was everything is only part of a greater whole. Of course, the multiverse is controversial. Some scientists argue that it lies beyond testability, that universes outside our own cannot be observed, and so the idea is metaphysical rather than scientific. Others counter that the multiverse is not an arbitrary speculation, but a prediction of models that are themselves testable. If inflation is confirmed, and if its mathematics naturally leads to eternal inflation, then the multiverse follows whether we like it or not. It is not a theory invented for convenience, but a consequence we must face, whether real or not. the concept reshapes our thinking. It forces us to consider that our universe may not be the only possible one, that the laws of physics we observe may not be fundamental but local, determined by the conditions of our bubble. Other bubbles may follow other laws, and only in those where the conditions allow complexity can observers like us arise. This idea, called the anthropic principle, is controversial, but it flows naturally from the multiverse picture. We see this universe not because it is the only one, but because it is one of the rare ones where beings like us can exist. As we continue through this chapter, the multiverse will deepen in complexity. We will explore how eternal inflation unfolds, how bubble universes collide, and how quantum physics ties the entire landscape together. For now, it is enough to recognize that inflation, born as a solution to cosmological puzzles, has grown into one of the most audacious visions of all, a cosmos where universes themselves are countless, and where the question of before is answered by the endless fertility of the multiverse. To grasp eternal inflation, we must first revisit how inflation itself works. Imagine a field of energy pervading space, called the inflaton field. In its highest state, this field drives rapid expansion. Eventually it decays, releasing energy that becomes the hot plasma of a Big Bang. But in many models, the field does not decay everywhere at once. It is a probabilistic process. In one region, it falls and expansion slows, creating a bubble universe like ours. In another region, it remains high, and inflation continues. The inflating regions grow faster than the bubbles, ensuring that even as bubbles form, the overall expansion never stops. The result is a self-reproducing cosmos, where inflation feeds itself eternally. Each bubble universe begins with a hot Big Bang, but its details depend on the local outcome of the inflaton field. The constants of nature, the number of dimensions, even the structure of particles may vary from bubble to bubble. Our universe is one realization among uncountable possibilities. The multiverse is not a uniform sea but a mosaic, each tile painted with different laws. From afar, the landscape is infinite. From within, each universe sees only its own bubble, unaware of the rest. This vision is dizzying. It means that reality is larger than our imagination has ever dared. It means that our observable universe, with its galaxies and stars, is only a drop in a boundless ocean. And it means that the Big Bang was not the unique moment of creation, but one of countless births happening across the multiverse. Time itself may stretch without beginning, with bubbles forming forever in the eternal swell of inflation. Such a cosmos raises unsettling questions. If universes are countless, then what does it mean for our own to exist? Is it special, or is it just one among an infinite crowd? Some thinkers embrace the anthropic principle. We observe this universe because it is one of the few where conditions allow observers. If the laws here permit stars, chemistry, and life, then naturally we find ourselves here. Other universes may exist with no structure, no light, no life. They are real, but forever silent. The anthropic principle is controversial. To some, it feels like surrender, an admission that science cannot explain why our universe has the properties it does. To others, it is an honest recognition of selection bias. Just as a fish cannot wonder why it lives in water rather than air, we cannot wonder why we live in a universe compatible with life. It could not be otherwise. In the multiverse, the conditions we see are not surprising. They are inevitable. The possibility of collisions between bubble universes adds another layer of intrigue. If bubbles form in an inflating sea, then sometimes they may bump into each other. Such collisions could leave imprints in the fabric of space, scars written into the cosmic microwave background. Some scientists search for these signatures, patterns of circular anomalies that could betray an ancient clash with another universe. None have been confirmed so far, but the search continues. If such evidence were found, it would revolutionize our view of reality, proving that our universe is not alone. Even without direct collisions, the mathematics of eternal inflation suggests that the process is unstoppable. As long as the inflaton field exists, inflation continues somewhere, spawning new universes endlessly. This means that creation is not a one-time event, but a perpetual process, a cosmic machine that never ceases to produce new realities. The word eternal is not poetic exaggeration. It is a literal description of a process without end. The philosophical impact of this idea is immense. For centuries, humans have asked why the universe exists. If the multiverse is real, the question may change. Instead of why this universe, we ask why this particular bubble. Instead of why existence, we ask why this version of existence. Some find this comforting because it means the mystery of fine-tuning dissolves into probability. Others find it troubling because it seems to rob our universe of uniqueness. The multiverse also challenges the limits of science itself. By definition, other universes may lie beyond our horizon, unreachable even in principle. Can science speak of things we cannot observe? Some say no, insisting that physics must confine itself to testable predictions. Others say yes, arguing that if the theory that produces the multiverse also makes testable predictions within our own universe, then the multiverse is a legitimate implication. This debate is not only about physics but about the philosophy of science, about what counts as knowledge and what lies beyond. As we stand at this frontier, it becomes clear that eternal inflation reshapes the question of before. The Big Bang was not the beginning of everything. It was the local event that created our bubble. Beyond it, before it, alongside it, inflation continues. The word before regains meaning, not as time before time, but as universes before ours. We are one chapter in an infinite book, one bubble in an endless froth, one possibility realized among countless others. To live in a universe born of eternal inflation is to inhabit a paradox. On one hand, our cosmos feels vast beyond comprehension, filled with galaxies, stars, and worlds. On the other hand, in the context of the multiverse, it is a single bubble adrift in an infinite sea. What feels complete is only partial. What feels whole is only local. The grandeur of the observable universe shrinks when set against the unending fertility of inflation. This realization unsettles our sense of significance. If universes are countless, what makes ours special? Perhaps nothing. Perhaps it is only one among endless variations, a cosmic accident whose laws allow chemistry, stars, and life. In an infinite ensemble, even the improbable becomes inevitable. Every combination of constants, every arrangement of matter, every possible history may unfold somewhere in the multiverse. In that vision, we are not unique. We are one realization of possibility, one flower blooming in an infinite field. Some thinkers resist this vision, fearing it dissolves meaning. If everything happens somewhere, then what weight do our choices carry? If copies of us exist in other universes, living other lives, then what is the value of this life? Yet others argue that meaning is not diminished, but deepened. The rarity of our conditions, the improbability of our emergence, becomes all the more remarkable. To live in a universe where life is possible is extraordinary, even if countless other universes are barren. Our existence gains poignancy from its contrast with the silence beyond. Science, for its part, continues to search for traces. The cosmic microwave background is scrutinized for anomalies that could signal a collision with another bubble. Gravitational waves are studied for whispers from inflation's earliest moments. The distribution of galaxies is mapped for patterns that could betray physics from beyond our bubble. None of these searches have yet yielded confirmation, but the pursuit itself expands our vision. It pushes us to ask questions once confined to philosophy. What is real? What can science know? What lies beyond observation? Even if direct evidence remains elusive, eternal inflation reshapes cosmology in a fundamental way. It provides a framework where the question of before is no longer meaningless. Our Big Bang is not the boundary of existence but one of its many blossoms. The multiverse is not a speculative add-on, but a natural consequence of inflationary models. If inflation is true, then eternal inflation may follow. And if eternal inflation is true, then the multiverse is real, whether we can observe it or not. The infinity of the multiverse challenges the limits of reason. Infinity is not just a large number, it is the absence of number. It swallows counting, undermines probability, and blurs definition. If every possibility occurs somewhere, how do we assign meaning to probability at all? How do we say something is likely or unlikely when all outcomes are realized? Physicists wrestle with these questions, devising ways to regulate infinity, to tame the measure problem, to define likelihood in an endless ensemble. But the mathematics remains unfinished, and the philosophical weight remains heavy. Perhaps the greatest shock of eternal inflation is its humility. It tells us that our universe, once thought to be everything, is not central, not unique, not even complete. Just as Copernicus showed that the Earth is not the center of the cosmos, just as Hubble showed that the Milky Way is not the only galaxy, eternal inflation shows that our universe is not the only universe. Each step pushes us further from the illusion of centrality, further into the vastness of reality. And yet, in this humility, there is wonder. To live in one bubble among countless others does not make our bubble less real. It makes it part of a greater whole. To imagine universes blooming endlessly is to glimpse a reality richer than any single cosmos could provide. It is to see creation not as a singular event, but as a perpetual flowering, a timeless fertility written into the fabric of existence. As we leave this chapter, we carry with us the image of bubbles budding in an eternal sea, each expanding into its own reality, each carrying its own history. Our universe is one such bubble, our Big Bang one such birth. What came before is answered not with silence, but with infinity. Beyond our horizon, universes multiply forever. Before our beginning, inflation already stirred. The question of before dissolves into a landscape without end, where creation is not unique, but eternal. And yet, even eternal inflation leaves mysteries unresolved. For if universes bloom endlessly, what is the soil that nourishes them? What is the framework in which inflation occurs? What deeper laws govern the multiverse itself? To approach those questions, we must turn to the search for quantum gravity, the attempt to unify relativity and quantum mechanics, and to peer into the structures that lie beneath space-time itself. At the edge of the Big Bang, where densities soar and temperatures rise beyond imagination, the known laws of physics fall silent. General relativity, Einstein's great description of gravity as the curvature of space-time, works beautifully for stars, galaxies, and black holes. Quantum mechanics, the strange but accurate framework of the subatomic world, governs particles, atoms, and forces with uncanny precision. Yet when the two must meet, at the singularity of the Big Bang, or inside the heart of a black hole, they clash. Their equations refuse to unite. Infinity appears, certainty vanishes, and understanding collapses. To go further, we need a new theory, a theory of quantum gravity. Quantum gravity is the quest to merge the smooth fabric of relativity with the granular uncertainty of quantum mechanics. It seeks a single description where space-time itself is not continuous but quantized, built from fundamental units, the way matter is built from atoms. In this vision, space and time are not the backdrop of reality, but emergent features, woven from more basic elements. Just as water emerges from molecules yet behaves differently than molecules alone, space-time may emerge from deeper building blocks. One approach is loop quantum gravity. In this framework, space-time is not infinitely divisible, but composed of tiny loops woven into a network. These loops form a spin foam, a structure that evolves as the universe evolves. Distances and areas are quantized, meaning there is a smallest possible unit of space, a smallest possible unit of area, a smallest possible unit of volume. In loop models, singularities are avoided because space-time cannot shrink to zero. Instead, when densities reach the Planck scale, the structure of space-time resists further compression, and a bounce occurs. This leads to a radical possibility. The Big Bang was not the beginning, but a transition, a rebound from a previous contraction. The singularity dissolves, replaced by a bridge between universes. Another approach is string theory, which suggests that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. Each vibration corresponds to a particle, much like different notes on a violin string produce different sounds. Strings require extra dimensions to be consistent, dimensions beyond the three of space and one of time we experience. In some versions, these dimensions are curled up, hidden from view. In others, they stretch into higher dimensional branes, surfaces that may collide and create universes. The ekpyrotic theory of cyclic cosmology emerges from this idea, where brane collisions ignite new Big Bangs. String theory offers a framework where our universe is one possibility in a vast landscape of configurations, each corresponding to a different arrangement of dimensions and vibrations. The holographic principle adds another astonishing perspective. Inspired by black hole physics, it suggests that the information contained in a volume of space can be described entirely by data encoded on its boundary. In other words, the three-dimensional universe we experience may be like a hologram, a projection of information stored on a two-dimensional surface. If this principle is correct, then space-time itself is not fundamental but emergent from underlying information. The Big Bang, in this view, may be understood not as the origin of space and time but as the unfolding of information into geometry. What all these approaches share is a refusal to accept the singularity as the end of explanation. Where relativity halts, quantum gravity begins. Singularities are not physical objects, but signs that our description is incomplete. By replacing them with quantum structures, we regain continuity, not of space-time itself, but of understanding. Instead of the impossible infinity of a singularity, we have loops, strings, or holograms, each offering a path through the mystery. The implications are profound. If loop quantum gravity is correct, then our universe may be only the latest in an endless chain of bounces. If string theory is correct, then our universe is one brane among many, perhaps colliding and rebounding in higher dimensions. If the holographic principle is correct, then our entire cosmos is the unfolding of information written on a distant screen. Each vision transforms the question of before into something new, something deeper, something stranger than intuition allows. But these theories are not yet complete. The mathematics is daunting, the predictions subtle, the evidence elusive. Experiments cannot yet probe the Planck scale, where these effects dominate. Instead, physicists search for indirect hints, patterns in the cosmic microwave background, signatures in gravitational waves, anomalies in black hole physics. Every clue matters, for at stake is not just the history of the universe, but the foundation of reality itself. Quantum gravity is more than a technical pursuit. It is the attempt to see what lies beneath existence, to find the language in which the cosmos is truly written. If relativity and quantum mechanics are two dialects, quantum gravity is the unified tongue from which both emerge. To discover it would be to hear the universe speak more clearly than ever before, to follow its story not just to the beginning but through it. To imagine space-time as quantized is to reframe the very canvas of reality. In the smooth geometry of relativity, space can be divided endlessly, and time flows continuously like an unbroken river. But in loop quantum gravity, this image is replaced by a granular structure. Just as a painting appears smooth from a distance but reveals individual brushstrokes up close, so too space-time may reveal discrete quanta when viewed at the Planck scale. In this framework, there is no such thing as infinite density. The loops of geometry resist compression beyond a certain point, producing a bounce rather than a singularity. This changes the narrative of the Big Bang. Instead of a universe born from nothing, we have a universe rebounding from a prior state. Contraction does not end in destruction, but in transformation. Expansion does not begin from emptiness, but from a quantum bridge. The very concept of before becomes redefined. There was a before, but it was not a mirror image of our universe. It was a contraction governed by the same laws that gave rise to our current expansion. The mathematics of loop quantum cosmology is complex, but its implications are poetic. The singularity that once marked the boundary of explanation dissolves into a passage, a throat connecting universes. The Big Bang becomes the Big Bounce. Our cosmos is not the first, and perhaps not the last. Time does not begin. It oscillates. String theory offers a different but equally astonishing vision. In this framework, the universe is composed of vibrating strings, their harmonics giving rise to particles, forces, and even space-time itself. Unlike loops, strings cannot exist in just 4 dimensions. They require additional spatial dimensions, usually 6 or 7, hidden or compactified in ways that make them invisible at our scale. These extra dimensions create a vast landscape of possible universes, each with its own physical laws, constants, and properties. One branch of string theory suggests that our universe is a brane, a 3-dimensional surface embedded in a higher dimensional space. Other branes exist alongside ours, floating like sheets in a vast higher dimensional arena. When branes collide, the impact can release enormous energy, igniting a Big Bang and creating a new universe. This is the ekpyrotic scenario, where cosmic history is driven by collisions in higher dimensions. If true, our universe was not created in isolation, but as the product of a grander choreography of branes, colliding, rebounding, and colliding again in a cycle of creation. The holographic principle adds yet another layer. It suggests that what we perceive as 3-dimensional reality may be encoded on a 2-dimensional boundary. The analogy is a hologram, where a flat surface carries information that appears as a 3-dimensional image. In the same way, the volume of the universe may be a projection of information written on its boundary. Black hole physics inspired this idea, showing that the information content of a black hole is proportional not to its volume but to the area of its horizon. If this principle applies to the entire universe, then our cosmos is a projection, an emergent phenomenon arising from information. In that case, the Big Bang was not the creation of space and time, but the decoding of information into geometry. What unites these visions is the idea that space and time are not ultimate. They are emergent, like temperature or pressure, arising from more fundamental elements. Just as molecules give rise to the sensation of heat, deeper structures give rise to space-time. This means that asking what came before the Big Bang may be like asking what came before heat existed. The question changes when we recognize that time itself is a secondary property, not a fundamental one. Yet quantum gravity remains incomplete. Loop models are elegant, but lack full unification with other forces. String theory is mathematically rich, but has not yet produced unique, testable predictions. The holographic principle is profound, but still a guiding principle rather than a complete framework. The search for evidence is ongoing. Physicists look for imprints of a bounce in the cosmic microwave background, for patterns that might betray higher dimensions, for anomalies in black hole evaporation that could reveal holography at work. Each clue brings us closer, but the full picture remains hidden. Even so, the pursuit itself transforms the question of before. It moves us beyond the singularity, beyond the despair of infinite density, into a realm where new structures carry the story forward. It suggests that the universe has deeper layers, that our familiar dimensions are the surface of a more intricate design, and it shows that to understand the beginning, we must not only look back in time, but also inward into the foundations of reality. Quantum gravity is not just the next step in physics. It is the attempt to see the cosmos from outside itself, to glimpse the scaffolding upon which existence is built. If we succeed, we may find that before is not meaningless after all. It may be encoded in loops, strings, or holograms, waiting to be revealed by the mathematics of the future. The search for quantum gravity is not only a technical endeavor, it is also a philosophical crossing, a place where physics begins to blur into questions of meaning. To say that space-time is emergent, that the universe is woven from loops or strings or information, is to challenge the way we think about reality itself. It forces us to see the Big Bang not as a singular beginning, but as an interface between layers of description, the visible skin of a deeper structure. Consider again the singularity that general relativity predicts at the start of time. In relativity alone, densities climb without bound, equations collapse into infinities, and nothing further can be said. But infinities in physics are not realities. They are signals of incomplete theory. Just as the ultraviolet catastrophe in 19th century physics was resolved by quantum mechanics, so too, the singularity may be resolved by quantum gravity. Instead of infinite density, we may find loops, strings, or holographic data. Instead of an edge, we may find a bridge. Loop quantum gravity suggests that time stretches beyond the Big Bang, bending around the bounce like a curve that continues past what once looked like a cliff. String theory suggests that our universe is only one configuration in a vast landscape of possibilities, birthed perhaps by collisions of brains or by transitions in higher dimensions. The holographic principle suggests that our three-dimensional cosmos is the projection of information, that the Big Bang was the unfolding of data written on a boundary beyond our perception. Each of these visions removes the singularity and replaces it with a structure, a mechanism, a meaning. And yet, in their variety, these theories also highlight our ignorance. Which, if any, is true? Which captures the actual foundations of reality? Evidence remains scarce, for the Planck scale is far beyond our experimental reach. We cannot yet build instruments powerful enough to probe it directly. We must rely on indirect signs, on whispers from the early universe, on patterns in the cosmic microwave background, on the behavior of black holes as they evaporate. Every observation is precious, every anomaly a possible clue, but the definitive evidence remains ahead of us. Still, even without certainty, the pursuit itself changes the question of before. Instead of seeing the Big Bang as a wall, we see it as a veil. Behind the veil may lie a previous universe, a higher dimensional brain, or a holographic screen. Behind the veil may lie the true architecture of reality, where time is not fundamental but emergent, where existence itself is information, where what we call before is simply another way of saying deeper. Here, physics brushes against philosophy. If time is emergent, then our notions of causality, sequence, and history are not ultimate but approximate. If reality is holographic, then our experience of three dimensions is a projection, no more fundamental than the flicker of an image on a screen. If universes bounce or collide, then our own is only a chapter in a story that has no first page. These are not only scientific models, they are philosophical provocations, reshaping how we think about existence. The deeper we follow this path, the more we see that the origin of the universe may never be described in simple terms. It may not be a single event, but a transformation of frameworks, a shift from one layer of reality to another. The Big Bang may be like the surface of water, hiding the molecular dance beneath. Quantum gravity is the attempt to dive beneath the surface, to see what truly churns below. Perhaps when the theory is complete, we will learn that the question of before was misphrased all along. Not what came before, but what structure underlies. Not what preceded time, but what gives rise to time. In this way, physics transforms the question, turning it from an unanswerable puzzle into a doorway to deeper understanding. As this chapter closes, we stand at the threshold where physics and philosophy meet. We glimpse a universe where loops, strings, and holograms replace singularities, where space-time itself is not absolute but emergent, where before is not meaningless but reframed. To continue, We must ask whether time itself is fundamental, or whether it is an illusion, a shadow cast by deeper processes. To that question, we now turn as we explore the idea of timeless existence. We move now into the most unsettling possibility of all, one that strips away even the comfort of time itself. For much of human history, time has been taken as the most basic reality. We mark our lives by its flow, we measure change against its rhythm, and we imagine the universe as unfolding upon its stage. But what if time is not the stage? What if time is the play? What if time is not fundamental at all, but emergent, a secondary property of deeper laws that exist without it? To imagine timelessness is to confront the limits of language. Our words depend on sequence. Sentences unfold, one after another, just as thoughts do. To describe a reality without time is like trying to describe color to someone who has only known black and white. Yet physics itself points us in this direction. The Wheeler-DeWitt equation, a cornerstone of attempts to merge relativity and quantum mechanics, contains no time variable at all. It describes the quantum state of the universe not as something that evolves in time, but as something that simply island time does not appear in the equation. Reality, in this view, is a frozen wave function, a timeless whole. How then do we experience time? If the universe at its deepest level is timeless, why do we live within the flow of past, present, and future? The answer may be that time is emergent, not fundamental. Just as temperature emerges from the collective behavior of molecules, time may emerge from the correlations between events. In this view, time is a macroscopic phenomenon, real to us, but not basic to the universe. Carlo Rovelli, a physicist of loop quantum gravity, has argued that time as we know it may be an illusion, a convenient description that arises only at certain scales. At the most fundamental level, there are only relations, only correlations between states. What we call before and after are ways of describing patterns in those correlations. Our brains interpret these patterns as flow, but the underlying reality is static. The river of time is a perception, not a substance. This idea is deeply unsettling because it means that change itself may be an illusion. Our sense of becoming, of events unfolding, of history moving forward, may not reflect ultimate reality. Instead, reality may be a timeless whole, a block universe where all events past, present, and future coexist. In this picture, your birth, your life, and your death all exist simultaneously, like frames of a film. Time is not the film itself, but the way consciousness experiences the frames in sequence. The implications for the Big Bang are profound. If time is emergent, then the question of before the Big Bang dissolves. Before belongs to the emergent level, not the fundamental one. At the deepest level, there was no before and after, only the timeless state of the universe. The Big Bang is not the first moment, but the point where time itself crystallized out of timelessness. Yet timelessness need not mean lifelessness. The Wheeler-DeWitt equation, though static, contains the potential for dynamics. Observers within the universe, using internal clocks made of matter and motion, can perceive change relative to themselves. In this way, time is not absent, but relative, not universal, but local. Different observers, in different contexts, construct their own experiences of time from the same timeless whole. To live in such a universe is to inhabit a paradox. We experience time as the most immediate reality, yet it may be the most illusory. We cling to past and future, yet they may be constructs of perception. We fear endings, yet in a timeless whole nothing ever truly ends. Everything simply island. This vision is both terrifying and liberating. Terrifying because it robs us of the flow we take for granted. Liberating because it suggests that existence is eternal in a deeper sense, that nothing truly passes away, that every moment is forever inscribed in the fabric of reality. As we continue through this chapter, we will explore how timelessness reshapes our understanding of existence, how physics leads us to the edge of philosophy, and how the deepest question, what existed before the universe, may be dissolved rather than answered. For if time itself is emergent, then before may never have existed at all. If the universe at its deepest level is timeless, then what we call the flow of time must be explained in terms of perception. The Wheeler-DeWitt equation suggests a frozen universe, a quantum state that simply exists without reference to past or future. How, then, do beings like us come to experience the world as dynamic, with events unfolding and moments slipping away? The answer may lie in the relationship between parts of the universe, rather than in any universal clock. Consider a book. The entire story exists all at once, printed on its pages. There is no literal before and after in the book itself. Those sequences arise only when a reader turns the pages. The universe may be similar. At the fundamental level, all events exist together in a timeless structure. Our consciousness plays the role of reader, interpreting events in order, creating the sensation of flow. To us, time feels absolute. To the universe, it may not exist at all. Physicists call this the problem of time. In quantum gravity, there is no single variable that corresponds to time. Instead, time must be reconstructed from change within the system. A clock is nothing more than a subsystem whose state we use to measure the state of another subsystem. For example, the oscillations of a cesium atom define a second. But in a timeless universe, there is no external clock. There are only correlations. When one subsystem changes, we describe another subsystem as having evolved relative to it. Time, then, is relational. It is not fundamental, but a way of describing consistency between changes. This picture dissolves the idea of a universal now. In relativity, simultaneity was already relative. What is simultaneous for one observer may not be for another. In a timeless framework, even the flow of now disappears. There is no unique present sweeping across the cosmos. All events coexist, and what we call now is only the slice of reality our consciousness perceives. The past is not gone, and the future is not yet to be. They are all equally real, waiting in the block universe. The psychological weight of this idea is immense. If every moment exists eternally, then nothing is ever truly lost. The laughter of a child, the glow of a sunset, the sorrow of a farewell, all remain inscribed in the timeless whole. To us, they vanish into memory, but in the block universe, they endure. This thought can be both comforting and disturbing. Comforting because it means nothing ever truly ceases. Disturbing because it strips away the uniqueness of the present and the possibility of change. We live in the illusion of flow, while reality is frozen. Some thinkers argue that consciousness itself may be the engine of time. The brain processes events sequentially, weaving them into narrative. The sense of before and after may be a construction of neural activity, not a reflection of external reality. In this view, time is not discovered but created, a projection of the mind onto the timeless universe. If so, then our experience of time is as real as any perception, but it is not ultimate. It is a feature of biology, not of physics. Yet even within physics, timelessness does not eliminate dynamics. The Wheeler-DeWitt equation describes a static universe, but within that static whole, observers can trace paths. These paths, defined by correlations, give rise to apparent evolution. From inside the universe, time feels real because observers are part of the system, moving along trajectories that create the sense of flow. From outside the mathematics, there is only the whole, complete and changeless. The duality is striking. Time is both illusion and reality, both emergent and experiential. This view transforms the question of before. If time is emergent, then asking what came before the Big Bang may be like asking what is north of the North Pole. The question dissolves, not because there is no answer, but because the answer lies in a different framework. Before assumes time, and if time itself is emergent, then before never existed. What existed was the timeless whole, of which our Big Bang is a slice. Our universe did not begin in time. It began time. As unsettling as this is, it aligns with the trajectory of science. Time has been dethroned step by step. Newton saw it as absolute, flowing everywhere identically. Einstein revealed it as relative, bent by gravity and motion. Quantum gravity suggests it is emergent, not fundamental at all. Each step moves us further from intuition, further from the way we experience reality, and closer to the way reality actually island. In this light, our lives take on new resonance. We live in the flow of time, but that flow is an appearance. The deeper truth is timelessness. Yet within the illusion lies our experience, our choices, our stories. Illusions are not unreal. They are how reality manifests to us. Just as colors are the way our brains interpret wavelengths of light, time is the way our minds interpret correlations in a timeless universe. It is both illusion and reality, depending on the level at which we look. To imagine a timeless universe is to abandon the deepest habit of human thought. For millennia, we have assumed that everything moves through time, that existence itself is inseparable from the ticking of moments. Yet, if physics is correct, the foundation of reality may have no ticking at all. The universe may be a timeless quantum state, complete and unchanging, with time emerging only as an approximation, a shadow cast by deeper structures. The Wheeler-DeWitt equation embodies this vision. It is the central equation of canonical quantum gravity, uniting general relativity and quantum mechanics into a single framework. Strikingly, it contains no time variable. It describes the entire universe as a wave function, an object that encodes all possible configurations of space-time and matter. But this wave function does not evolve. It does not change. It's simply island. In this frozen formalism, all that ever happens is already contained. Our sense of passage from one moment to another is not a feature of the equation, but of observers within it, tracing correlations and constructing a narrative of flow. This picture suggests that reality is more like a vast, timeless landscape of possibilities than a movie that plays from beginning to end. We are not watching the film of the universe. We are characters within it, experiencing frames in sequence, convinced that the sequence is fundamental when it is not. The illusion is powerful because it is necessary for beings like us to make sense of change. Without the perception of flow, memory and anticipation would collapse, and with them, the structure of conscious life. But physics whispers that behind the perception lies a deeper stillness. If this is true, then the Big Bang is not the first moment in time, but the emergence of time itself. It is the crystallization of temporality out of timelessness, the point where the frozen whole begins to be experienced as flow. Asking what came before becomes like asking what lies outside the universe's geometry. There is no before, because time is part of what began. What existed was the timeless state, the universal wave function, the frozen whole that contains all histories at once. This does not mean that nothing happened. It means that happening itself is emergent. At the fundamental level, there is no sequence. But from the perspective of subsystems like us, sequences appear, clocks tick, and events unfold. The timeless state contains them all. Our lives, our histories, our civilizations are woven into it. They are real to us, and yet they are emergent patterns within a greater timelessness. The philosophical implications are staggering. If the universe is timeless, then eternity is not an endless stretch of moments, but the absence of moments altogether. Immortality is not life extended forever, but existence outside time. Death does not erase moments, because moments were never flowing to begin with. They simply are, inscribed in the timeless whole. In this sense, nothing is ever lost. Everything that has ever been is eternal, not because it persists through time, but because time itself is an appearance. Some physicists speculate that consciousness plays a special role here. Our perception of time may not merely be a byproduct of physics, but an active construction of the mind. The brain stitches together sensory input into narratives, filtering timeless correlations into temporal sequences. In this sense, time is as much a cognitive phenomenon as a physical one. The arrow of time, tied to entropy, gives our perception its direction, but the deeper reality may be symmetric, timeless, and whole. This vision unsettles because it robs us of beginnings and endings. We want to know where we came from and where we are going. We want to measure progress and anticipate futures. Timelessness erases those comforts, yet it also offers a strange peace. If every moment exists eternally, then our lives are not fleeting sparks in darkness. They are part of an eternal tapestry, woven into the fabric of reality forever. The laughter of a child, the fall of a leaf, the rise of a star, none of these vanish. They are eternal in the timeless whole. And so the question of before dissolves once again. If time itself is emergent, then before is not a meaningful concept. The universe did not arise from nothing in time. It arose from timelessness into time. What we seek when we ask what came before may not be a sequence, but a structure. Not a cause, but a foundation. That foundation, physics suggests, may be timeless existence itself. As this chapter closes, we find ourselves at the limits of language and imagination. We have moved from relativity to quantum mechanics, from bounces to multiverses, from loops and strings to holograms, and now to timelessness itself. Each step has redefined the question of before, shifting it from one horizon to the next. And yet, the mystery endures. For if timelessness is real, then perhaps the greatest secret of the universe is not how it began, but why it exists at all. Long before telescopes measured galaxies or equations traced the arc of space-time, humans gazed at the sky and wondered where it all came from. The night sky, studded with stars, inspired not only awe but questions. What brought this into being? Why is there something instead of nothing? These questions did not wait for physics. They were answered by story, by myth, by theology. Every culture on Earth has carried its own vision of creation, its own attempt to make sense of beginnings. In the ancient myths of Mesopotamia, creation often began in the struggle of gods. In the Babylonian Enuma Elish, the universe is born from the conflict between the god Marduk and the primeval sea goddess Tiamat. In the fragments of Egyptian tradition, the cosmos emerges from a watery chaos, with the sun rising from the first mound of Earth. In Hindu cosmology, cycles of creation and destruction stretch across unimaginable spans, with gods breathing universes into existence and withdrawing them again. In the Hebrew scriptures, the opening lines declare, "In the beginning, God created the heavens and the earth," presenting creation as the will of a single deity, shaping order from formlessness. These stories are not scientific in the modern sense. They do not propose testable hypotheses or predict cosmic microwave backgrounds. But they are profound in another way. They encode humanity's earliest attempts to confront the mystery of origins. They recognize that the question of beginning demands an answer beyond ordinary experience. Whether through gods, chaos, or cycles, they weave meaning into the cosmos, turning the night sky into narrative. Philosophers, too, have wrestled with the problem. In ancient Greece, some thinkers argued that the universe had no beginning. Aristotle taught that the cosmos is eternal, without creation or destruction, cycling endlessly. Others, like the atomists, suggested that the universe arises from the eternal motion of atoms in the void. Centuries later, Christian and Islamic philosophers wrestled with reconciling revelation with reason. Thinkers such as Augustine argued that time itself was created with the universe, echoing an intuition that physics would only confirm millennia later. In the Islamic tradition, scholars debated whether the universe was created in time or existed eternally alongside God. Each argument reflects the same tension we feel today. Does the universe have a beginning, or is it eternal? What distinguishes theological and philosophical approaches from scientific ones is not only method, but purpose. Science seeks explanations grounded in evidence, in observations that can be tested and repeated. Religion and philosophy seek meaning, coherence, and moral orientation. To ask why the universe exists in philosophy or theology is not merely to ask about mechanisms. It is to ask about purpose, intention, value. To ask why in science is to ask about laws, causes, and structures. The same word spans two domains, but it means very different things in each. The tension between these approaches has sometimes erupted into conflict. When Galileo turned his telescope to the sky and saw moons orbiting Jupiter, his discovery challenged religious authorities who insisted that the Earth was the unmoving center of creation. When Darwin proposed that life evolved through natural selection, his theory clashed with literal readings of sacred texts. Yet, the tension is not inevitable. Many thinkers, then and now, see science and religion as addressing different aspects of the same mystery. Science tells us how the universe works. Religion and philosophy tell us what, if anything, it means. At the heart of both is the same awe before existence. Whether we speak of God commanding light into being, or of quantum fluctuations birthing space and time, we are grappling with the same ultimate question: why is there something rather than nothing? Science may describe the mechanisms, but it cannot explain why those mechanisms exist. Religion may describe the purpose, but it cannot explain how the mechanisms work. Both point to a horizon of mystery that neither can fully cross. In our own time, this tension has sharpened with the rise of cosmology. The Big Bang model, now supported by overwhelming evidence, declares that the universe has a finite age, about 13,800,000,000 years. For some, this echoes the religious idea of creation in time. For others, it contradicts eternal cosmologies. Yet even here, science does not prove theology right or wrong. It simply describes what observations demand. Whether those observations are interpreted as divine creation or as natural process depends on perspective. The interplay of science, religion, and philosophy is not competition, but dialogue. Each offers insights the others cannot. Science reveals the structure of reality in extraordinary detail. Religion offers frameworks of meaning that bind communities and individuals to existence. Philosophy tests the logic of both, probing their assumptions and their limits. Together, they circle the same abyss, the same unanswerable depth, the same haunting question of origin. As we continue through this chapter, we will explore how these perspectives intersect and diverge. We will see how myths of creation echo in modern cosmology, how theology confronts the implications of science, and how philosophy bridges the gap by reminding us that every answer raises deeper questions. For the mystery of before belongs not only to physics, it belongs to humanity's oldest search for meaning. When we look across the traditions of the world, the diversity of creation stories is astonishing, yet certain themes repeat with almost uncanny similarity. Many myths begin with chaos, a primordial formlessness, a void, a dark ocean. Out of that chaos comes order, whether by the command of a deity, the struggle of gods, or the natural unfolding of cycles. In Greek myth, chaos gives birth to Gaia and Uranus, earth and sky. In Norse tradition, the world emerges from the yawning void of Ginnungagap, where fire and ice meet. In Egyptian lore, creation arises from the waters of Nun, with the first mound of land rising from the flood. Over and over, cultures imagined that before creation there was not nothing in the strict sense but a kind of fertile chaos, a potential waiting to be shaped. This resonates strikingly with modern cosmology. The quantum vacuum of physics is not a true nothing, but a restless sea of fluctuations. It is chaotic, uncertain, fertile, with possibility. From it, universes may arise. The difference lies not in the imagery, but in the method. Myths describe chaos as story. Physics describes it as mathematics. Both recognize that absolute nothingness may be unthinkable, that what comes before order must be a fertile void. Religious traditions, however, often go further by tying creation to purpose. In the Abrahamic traditions, creation is not just a physical event, but an act of will. God speaks, and the universe comes into being. Light is commanded, order is imposed, and meaning is woven into creation itself. In Hindu cosmology, cycles of creation and destruction are not arbitrary, but expressions of divine rhythm, the breathing in and out of Brahma, the dance of Shiva. In Buddhism, while the universe may cycle without beginning, the focus shifts from cosmology to liberation. The impermanence of all things is a lesson in detachment. In each case, the story of creation is not only about how, but about why. Philosophers have long struggled with the idea of nothingness. Can nothing truly exist? When we say nothing, do we mean empty space, or the absence of even space and time? Martin Heidegger framed the question starkly: why is there something rather than nothing? For him, the mystery of being is irreducible, the deepest question of all. Other philosophers argue that nothing is incoherent, that even to imagine it is to think of something. If nothing is unstable or impossible, then something must exist. This line of reasoning anticipates some of the claims of modern cosmology, where the quantum vacuum cannot help but fluctuate. In contrast, religious traditions often embrace nothingness as a canvas for divine action. In the Hebrew and Christian scriptures, God creates ex nihilo, out of nothing. This is not nothing in the physicist's sense, but absolute nothingness, the absence of all, except the divine. In this way, creation is not the unfolding of potential, but the pure gift of existence. It is not necessary, not inevitable, but intentional. Theologians argue that this preserves the contingency of creation, that the universe need not exist but does, because it is willed into being. Science, of course, does not address divine will. It can only describe mechanisms. But the tension between these views highlights their different domains. To say that the universe arose from quantum fluctuations is not to deny theology. It is to describe how, not why. To say that God created from nothing is not to deny cosmology. It is to describe why, not how. The conflict arises only when one domain insists on replacing the other. Still, the dialogue is not without friction. When cosmologists speak of a universe from nothing, critics from theology and philosophy often object that the nothing described is not true nothing. It is already something, governed by laws, structured by mathematics. To them, such a vacuum is simply another kind of being. The physicist may respond that true nothingness is not coherent, that even laws themselves may emerge naturally, that existence is the default rather than the exception. Here, the lines blur, and debate shades into metaphysics. What becomes clear is that both science and religion circle the same abyss. Both face the unanswerable depth of why there is something rather than nothing. Both provide responses, shaped by their methods and assumptions. Science offers laws and mechanisms. Religion offers will and purpose. Philosophy reminds us that each response may be partial, provisional, unable to capture the whole. The mystery remains, inviting humility. As we continue this chapter, we will see how modern theology engages with the discoveries of cosmology, how some embrace the Big Bang as confirmation of creation, while others see it as irrelevant to faith. We will also explore how philosophy navigates the middle ground, asking whether science and religion are truly in conflict, or whether they are two languages, speaking of the same mystery from different vantage points. Modern theology has responded to the rise of cosmology in diverse ways. For some religious thinkers, the Big Bang is seen as a scientific confirmation of the ancient belief in creation. If the universe has a finite age, if time itself began 13,800,000,000 years ago, then perhaps this aligns with the declaration that in the beginning, the heavens and the earth were made. The finiteness of cosmic time seems to echo the finiteness of creation in Scripture. Others caution against such quick harmony. Science is provisional, always open to revision. To ground theology in a particular model of cosmology is to risk collapse when the model changes. If tomorrow new evidence revises the age of the universe or suggests that it cycles eternally, theology cannot be left adrift. For this reason, many theologians insist that creation is not about a scientific mechanism, but about the dependence of the universe on something beyond itself. Whether the cosmos began in a Big Bang or whether it has cycled forever, it still calls for explanation. Why does it exist at all? Why do laws and conditions allow anything rather than nothing? Creation, in this sense, is not a moment but a relationship. Philosophy sharpens this further. The cosmological argument, in various forms, has long suggested that everything contingent requires a cause. If the universe is contingent, then it requires something necessary to explain it. Some identify this necessary being with God. Others argue that the universe may itself be necessary, that no external cause is needed. Still others suggest that the question may be malformed, that asking why there is something rather than nothing assumes categories that may not apply. Each argument reflects an attempt to grapple with the limits of reason. Even atheistic philosophers admit the difficulty of absolute nothingness. To say that nothing could exist may itself be incoherent, for even the concept of nothing is a thought, a something in the mind. To imagine nothing is already to conjure something. Perhaps, they suggest, existence is the default state, the baseline condition. Perhaps it is more natural for something to exist than for nothing to exist. This inversion of intuition mirrors the claims of some physicists who argue that the laws of quantum mechanics make existence inevitable. What unites all these perspectives is the recognition of limits. Science reaches a horizon where experiments cannot yet probe. Religion reaches a horizon where mystery is embraced as divine. Philosophy reaches a horizon where reason folds back upon itself. Each, in its own way, acknowledges that ultimate origins may be beyond human grasp. Yet each insists that the question is worth asking, that in asking it we deepen our sense of wonder. It may be that science and religion are not enemies, but partners in mystery. Science reveals the structures, the mechanisms, the astonishing detail of how the universe unfolds. Religion offers frameworks of meaning, grounding human life in relation to the cosmos. Philosophy tests both, probing their assumptions, questioning their coherence, reminding us that neither can claim totality. When we ask what existed before the universe, we are not only asking for physics, we are asking for meaning, we are asking for purpose, we are asking for place. This is why the dialogue persists. Even in an age of satellites and particle accelerators, myths of creation still resonate. Even in traditions where faith is strong, discoveries of cosmology inspire awe. The search for before is as much a human quest as a scientific one. It belongs not only to laboratories, but to temples, not only to equations, but to poems, not only to reason, but to imagination. And perhaps the deepest truth is that no answer will ever fully satisfy. If science proves that the universe arose from quantum fluctuations, we can still ask why quantum laws exist. If theology insists that God created ex nihilo, we can still ask why God exists. If philosophy argues that existence is necessary, we can still ask why necessity itself is real. Each answer pushes the mystery back but never eliminates it. The horizon recedes as we approach, leaving us with wonder as the final response. As this chapter closes, We see how science, religion, and philosophy converge, not in their answers, but in their recognition of limits. Each points to the depth of the mystery, to the abyss of before, to the impossibility of complete explanation. Each, in its own language, affirms that to exist at all is extraordinary. And so, as we turn to the next chapter, we leave behind the realm of stories and metaphysics and return to evidence, to the cosmic microwave background, to the imprints of ancient light, to the possibility that traces of what came before may still be written across the sky. Speculation is vast, but science demands evidence. A theory, without traces in reality, remains philosophy, however elegant. And so, cosmologists search the sky not only for the story of our universe, but for whispers of what might have come before. The greatest record we possess is the cosmic microwave background, the faint afterglow of the Big Bang itself. Released when the universe was only 380,000 years old, this light carries the imprint of primordial fluctuations. Inflation predicted exactly the patterns we see: tiny irregularities, stretched quantum ripples that later seeded galaxies and stars. But researchers look closer, searching not only for confirmation of inflation, but also for clues that might reveal whether our universe once bounced, collided, or emerged from deeper structures. One of the most promising signatures is polarization, especially the elusive swirls known as B-modes. These patterns could reveal the presence of primordial gravitational waves, ripples in space-time itself, echoing from the very beginning. A detection would strengthen the case for inflation and might even probe physics at scales where quantum gravity rules. Early excitement in 2014 faded when dust in our own galaxy was shown to mimic the signal. But the hunt continues with new, more sensitive instruments scanning the sky. Other potential clues lie in anomalies. The cosmic microwave background contains features that resist easy explanation: a cold spot larger than expected, alignments across vast distances, hemispheric asymmetries. Some scientists argue these may be statistical flukes. Others wonder whether they hint at collisions with other universes, scars of a larger multiverse etched faintly across our sky. Beyond light, gravitational waves promise another path. The LIGO and Virgo observatories have already confirmed Einstein's predictions by detecting mergers of black holes and neutron stars. But beyond those individual events may lie a faint background, a cosmic hum left over from the earliest instants. If we can detect it, perhaps with future space observatories like LISA, we may listen directly to vibrations older than light itself. Those ripples could reveal whether inflation happened, whether the universe once contracted, or whether extra dimensions played a role in its birth. Even the distribution of galaxies offers testimony. The cosmic web of filaments and voids traces the evolution of primordial fluctuations into today's structure. Careful surveys can test different models of the early universe and may reveal hints of processes beyond the standard Big Bang. Each galaxy is not only a starry island but also a data point, helping to reconstruct the physics of creation. And yet, we face limits. The cosmic horizon defines how far we can see, and some questions may always lie beyond it. If other universes exist, they may remain forever unobservable. If time itself is emergent, no signal can carry us into a region before it crystallized. We may find traces, but we may also discover that the footprints of before have been erased by the immensity of expansion. Still, the pursuit itself is extraordinary. That we can measure the universe's structure with such precision, that we can test ideas about epochs beyond direct observation, is a triumph of human curiosity. Whether or not we ever find decisive proof of before, the search expands our understanding, sharpening speculation into testable science. The night sky remains our archive, its light and gravity, carrying whispers from the dawn. In those whispers, we seek confirmation, contradiction, or surprise. And even if the deepest secrets stay hidden, the act of listening brings us closer to the mystery. For science does not guarantee answers, it guarantees the courage to keep asking. We have followed the universe from its fiery birth to the trembling edge of timelessness, from the evidence written in the sky to the myths whispered by our ancestors. At every turn, the same question has waited for us. What, if anything, existed before the universe? And yet, as we now stand at the end of this journey, the answer remains elusive, perhaps forever beyond reach. The Big Bang model tells us that our cosmos began 13,800,000,000 years ago in a hot, dense state. General relativity traces this beginning to a singularity, where equations break down and infinity erupts. But singularities are not answers. They are signs that our understanding is incomplete. The no-boundary proposal suggests that the universe is finite but without edge, like the surface of a sphere, where the idea of before simply does not apply. Quantum physics offers another view, where universes may arise spontaneously from fluctuations, or where bounces replace beginnings, each cycle giving way to the next. Inflation stretches these visions further, producing an eternal landscape where universes bloom endlessly, and ours is one bubble among countless others. Quantum gravity deepens the mystery. In loop cosmology, space-time is quantized, and the singularity is replaced by a bounce. In string theory, higher dimensional brains collide and separate, igniting new epochs. The holographic principle whispers that our reality may be a projection of information written elsewhere. Each of these visions shifts the question of before into new terrain. Not what came earlier in time, but what deeper structures give rise to time at all. And then comes timelessness. The Wheeler-DeWitt equation erases time from its mathematics, describing the universe as a frozen quantum state. Past, present, and future all coexist in a timeless whole. In this view, the flow of time is an emergent illusion, born of perception, not of reality. The Big Bang was not the first moment, but the crystallization of temporality itself. Before becomes a word without meaning, a question asked from within the illusion of time, about a reality that has none. Philosophy and religion remind us that this is not only a scientific puzzle but a human one. Myths of chaos, divine creation, or eternal cycles reflect the same awe that drives cosmology. Theologians speak of creation from nothing, philosophers of the impossibility of nothingness, scientists of fluctuations in the quantum vacuum. Each approach circles the abyss, seeking meaning, coherence, or evidence. None offers a final answer. All affirm the mystery. Perhaps the universe had no beginning. Perhaps it has always existed in one form or another. Perhaps it is part of a multiverse. Or perhaps it is timeless, a whole without before or after. Or perhaps the question itself dissolves when pushed too far, a mirror reflecting back the limits of human thought. We may never know, but to ask is to be human, to stretch our imagination into realms where language falters, to stand at the edge of reason and still gaze outward. As we close, imagine the night sky again. Light from galaxies billions of years away streams into our eyes, carrying the memory of beginnings we cannot fully comprehend. Behind that light lies the microwave glow of the first atoms. Behind that glow lies silence. Perhaps other universes. Perhaps timelessness. Perhaps nothing at all. The mystery remains, and it may always remain. But in the asking, in the searching, in the wonder itself, we find our place. What existed before the universe? Perhaps nothing. Perhaps everything. Perhaps the question has no answer. But it is in the asking, not the answering, that we touch the deepest mystery of existence.